So yeah, my first test of this NCY CDI was on the bike when it was pretty much stock. It actually went a mile per hour slower, which I thought was weird. And that was on several runs. It was 1 second slower in the 0 to 30. It was 1/10 slower in the 8th mile, and then 1 mile an hour slower on multiple runs. So the stock CDI wins. When you're doing performance parts, a lot of times they are going to make the bike slower unless you have the required performance in your bike. Like heavy valve springs. Heavy valve springs will take horsepower away. But if you can turn enough RPM to make extra horsepower, it makes up for it. I've got a cam in it. I've got a big bore kit. I've got a PWK smoothbore flat slide carburetor. So I think I've got enough performance stuff to justify the NCY CDI. And we're going to try it now, but I need to get a base run. This CDI is primarily a capacitor, hence the term capacitor discharge ignition, CDI. But in addition to being a capacitor, it can do some magic stuff. It has a gate switch in it, and the other magic trick is it can have a timing map in there to advance and retard timing. I just lied, but we'll get into that later. So I've got the stock CDI in it. The last time I did a top speed run, I think I was 70. This bike does anywhere between 68 and 73 miles an hour, depending on the day, I guess. So we call it 70. But since I'm going to do a back-to-back CDI run, I want to go get a base run with the stock CDI so I can run back home, change CDIs, make the same exact run and see if I got a difference. Unless you're a total nerd, the easiest way to think of electricity is like water. This is our wire coming out of the stator. It should be yellow. And this is producing electricity, and that's the electricity coming out. As you go to idle, electricity gets worse. Go full throttle, you get a lot of electricity, and then you go back down the throttle, it comes back, and so you get a very inconsistent flow of electricity. They call that a poor wavelength. And that kind of electricity is not good for electronics, such as light bulbs, computers, things like that. So we want a more steady flow of electricity. So introduce the capacitor. Imagine we can collect this electricity going into this capacitor, and as it fluctuates and flows and gets bigger and less, we don't care. We're gonna release the electricity in a constant stream. A nice 12-volt stream. That's 12 volts electricity pouring out of this capacitor going to all our electronics and doing a great job of maintaining everything. So we turn the light off. Electricity still going. Then we turn the whole motorcycle off. We've stopped the flow of electricity into this capacitor. If this is 6 to 13 volts coming out of that wire, this is about 200 to 400 volts. Now the vehicle's off. This capacitor is still full of electricity. That's why capacitors are so dangerous. You take one out, if you ground it, boom. Just got electrocuted by 400 volts. But imagine the CDI. We have a capacitor that's getting electricity at a random rate. Doesn't really matter. It's just filling. It's filling in less than 3 turns of that crankshaft, because on the 4th turn we want to dump all this electricity into the spark plug. Well, the coil. The coil's going to jack it up some more. That's a whole different subject. Imagine if we put a switch in here that just dumped all this electricity at once into the spark plug on that 4th hit. That's called a gate switch. When that trigger wire is activated by that little tab, the gate switch opens and it dumps. There's your high voltage going to your coil and then being jacked up and firing your spark plug. The flywheel is a direct extension of the crankshaft, so the flywheel is traveling this direction here. And as it spins around, it creates an electromagnetic field because there's copper coils inside here, which is a stator that produces electricity. The electricity is sent up this bundle. This wire on the face is your trigger. It goes to that gate, and it tells the gate to open and close. The faster this spins, the more electricity it produces. The trigger tells the CDI when this engine's at top dead center and ready for the spark plug to fire. So we're just going to go ahead and throw the coil out of the loop. We're not going to talk about that. So let's just say this goes pickup sensor, CDI box to spark plug. When I tell it to spark, I'm going to tell it by this little metal tab right here. This has got a magnetic pickup in it. That tab comes close enough to it that it hits it, and that's the signal right there. When that signal happens, it's going to send electricity up to the CDI. It's going to say on every 4th turn, it's going to say fire the spark plug. The problem with the system is that by the time this guy says fire the spark plug, and it goes to the CDI box, and it goes to the coil, and it goes to the spark plug, the piston's already past top dead center. We've already missed it. We have to tell it a little bit before that happens. Tell it to fire the spark plug before the piston gets to top dead center. That's called ignition advance. So how we're going to do that is mechanically, we're going to be able to adjust this tab. Let's say top dead center is here, for example. That's where we want to fire. Everything over here is before top dead center. Everything over here is after top dead center. It looks confusing because the engine's spinning this way. So as this comes around, top dead center is here. This is all the stuff that's happening before top dead center. So this is everything. Until once top dead center happens, all this stuff over here is happening after top dead center. So if I want to tell this thing to fire at top dead center, I've got to tell it to fire somewhere up in here. So by the time the signal gets to the spark plug, it happens at top dead center. So you can see the tab is welded on right there. So it hits that tab, it says fire the spark plug, and we keep rolling, and boom, top dead center happens at the same exact time that the signal gets to the spark plug, and it fires the spark plug. Problem is, we start speeding the engine up and go higher RPM. Now the signal's behind again. We need to advance the signal more. And when I say advance, it's weird. We're gonna go advance, means this side. Retard means this side. So now I need to advance the signal more because the engine's spinning faster. I was here and it was working good at idle. So now I need to go over here when I'm at 5,000 RPM. I need to tell it even earlier. How do you do that? Well, mechanical advance would be the ability to move this little tab around. So I can move this tab over here. And what they would do, let's say this whole flywheel floated somehow, and then reposition it. That's how mechanical advance works, and it uses vacuum to turn that. So typical numbers are, that engine guys know, is we're going to use 10 degrees before top dead center for idling, and then as we increase our RPM to about 2,000 RPM, we're going to move this metal tab over here to about 30 degrees before top dead center. We're just going to leave it at 30 degrees and let that be the open setting. But I can't move that tab. I can't re-weld it while I'm driving. That tab's fixed in place. And luckily this thing has an electronic ignition, so we can use that magic box. We've shown how this box is a capacitor and how it has a gate. You can also put some magic in this box, and that's the timing curve. We'll use this box to advance or retard timing. The pickup switch has to be positioned at a certain place on the flywheel. We know what position that is. We can electronically advance this timing, and we can tell it to fire before top dead center. All you electrical engineers just choked on your popcorn, because you know what I just said is a paradox. It's like the time travel paradox. You can't travel forward in time because the future hasn't happened yet. But you can travel backwards in time because the past has already happened. We want to advance timing. It can't be done electronically. If I try to make the spark happen here, it hasn't happened yet. If something hasn't happened yet, you can't move it forward in the future. So you cannot use a CDI box to advance timing, only to retard timing. If the signal happens here, it goes to the CDI, I can tell the CDI to wait a little bit before I release it. And then I can release it after top dead center. That's retarded. I can't release it before top dead center because I don't have it yet. I don't have the signal yet. And the CDI box has no idea which way this is rotating, so I can't tell it to rotate the other way. So there's the paradox. There is a solution to this conundrum. For a smart engineer, we know we can retard timing, but we can't advance it. So let's go ahead and weld this on mechanically, way advanced. I mean, further than it has to be. Then we can just retard timing to the advanced point we want. So even while we're retarding timing, it's going to advance it still because we haven't, let's say this tab's welded on 40 degrees advanced. So now if we retard timing 10 degrees, we have set timing at 30 degrees advanced. Genius, right? Again, typical timing curves: 10 degrees before top dead center advanced, at idle up to 30 to 34 degrees at 3,000 RPM, and all the way up to 10,000 RPM. So in a performance situation, we'd want to keep on advancing that timing. Us fast guys are running around at 10,000 RPM. We need more advance. Depending on how far forward this is welded gives us our range of advancement. So let's find out. Actual top dead center is marked on your flywheel, and it's right here, TDC. This little nub is welded right here. Well, that's a pretty far range. Now I have a degree wheel, but I think it covers the whole thing up. Use a protractor. So from TDC, that nub is welded 90 degrees before the pistons at top dead center. 90 degrees of advance before top dead center. Now, all we have to do is retard the ignition inside this box. Hey, release it after this many nanoseconds after this happens. So we typically want 10 degrees for idle, 30 degrees for regular cruising around. But since we're performance guys, we want to go 40 or 50 degrees, 40 to 50, somewhere in here. We want to really get that timing advanced because we're going to be running some high RPMs. We're going to be burning nitromethane that lights faster. Well, we've got a range up to 90. So we can actually have timing up in here. So this box could very well be performance, and it could very well give us timing up into this 40 and 50 range, make us have a faster, higher horsepower bike. The other thing this box can do for us is it can be an electronically bigger capacitor. That's what they claim they are also. They release more volts than a standard box. 200 to 400 more volts, they say, than a standard box. So we might be getting some unburned fuel and a weaker spark, and this would produce a strong enough spark to burn all the fuel. That's more torque. I didn't notice any improvement when I tried it on the stock bike, and I probably wouldn't because I'm not turning the RPMs or requiring a hot enough spark to justify running this. So if you have a stock bike, this is a useless piece, but now we're going to find out if it works on the performance bike. I held it open a little bit longer with the NCY. Didn't hit the same speed. Just like with the stock bike, it was slower. It'd be interesting to look at the GPS numbers, but on my GPS Speedo, it's definitely about 2 miles an hour slower.